There are 86 billion neurons in your brain. Inside every one of them is a tiny structure most people have never heard of, called a microtubule. In 1989, a Nobel Prize winning physicist named Roger Penrose said these structures are where consciousness actually lives. He said that what you are feeling right now in this moment is not just chemistry, it is quantum mechanics, the same strange physics that runs the smallest particles in the universe happening inside your head 40 times a second. For 20 years, almost everyone said he was wrong. But in the last few years, quantum experiments in labs around the world have started to suggest he might have been right all along. So what is really happening inside your head while you listen to this voice? Get comfortable, subscribe if you have not, and stick around, because the answer might change the way you think about being alive. Let's get into it. Part 1. The Book That Should Have Been Ignored. In the spring of 1989, a 68-year-old British mathematician sat down at his desk in Oxford and wrote a sentence that he must have known would get him in trouble. The mathematician's name was Roger Penrose. He had, by that point in his life, already collected the kind of credentials that should make a person immune from professional embarrassment. He had won the Wolf Prize in physics. He had proven, with a young Stephen Hawking in 1965, the first of the singularity theorems that showed black holes were not an artifact of idealized symmetry, but a robust prediction of general relativity itself. 3 decades later, that same work would earn him a share of the 2020 Nobel Prize. Roger Penrose was not a man at the edge of his field. He was, in the most measurable sense possible, near the centre of it. And in the book he was writing that spring, called The Emperor's New Mind, he was about to argue that almost everyone in artificial intelligence and almost everyone in neuroscience was making the same mistake. The mistake, as Penrose described it, was the assumption that the human brain is, at bottom, a kind of computer, a very impressive one, wet, warm, sloppy, made of neurons instead of transistors, but in the end, a machine that takes inputs, runs algorithms, and produces outputs. On that view, you're reading these words right now because patterns of electrical activity are propagating through 86 billion neurons connected by something on the order of 100 trillion synapses, and the patterns happen to correspond to comprehension. Consciousness, in this picture, is what those patterns feel like from the inside. And the reason you feel anything at all, on the strong version of the view, is just that the patterns are complicated enough. Any sufficiently elaborate computer would feel something too. Penrose said no. He said it with a mathematician's care, but he said it clearly. He said that there were specific kinds of things a human mind can do that no Turing machine, no matter how large, no matter how fast, could ever do. He pointed to a famous result that Kurt Gödel had proved back in 1931. A result so strange that it had quietly broken the foundations of mathematics for everyone willing to look at it. Gödel had shown that any consistent formal system rich enough to talk about basic arithmetic must contain statements that are true, but that cannot be proven inside the system. Penrose argued that human mathematicians could sometimes see the truth of such a Gödel statement directly, by stepping outside the formal system and looking at it from above. A computer could not. A computer could only run its programs. Therefore, Penrose concluded, the brain was doing something that no computer could ever do, and therefore the brain was not really a computer at all. The argument was contested almost from the moment the book left the printer. Philosophers and computer scientists lined up to point out, with varying degrees of patience, that Penrose was probably misreading what Gödel actually proved. Human mathematicians, they said, do make mistakes. They sometimes endorse statements they cannot prove. They sometimes endorse statements that are actually false. A computer with controlled errors could do the same thing. The Gödel argument was not the airtight knockout that Penrose seemed to think it was. The argument is still considered, in 1989 and right now in 2026, a minority view in the philosophy of mathematics. But the argument was the door. Penrose walked through it. Once he'd convinced himself that classical computation could not capture what the human mind does, he had to find some other piece of physics that might. And there was really only one place to look. There was, in the foundations of physics, exactly one phenomenon known to produce results that no algorithm could predict in advance. That phenomenon was the collapse of the quantum wave function, the strange, still not fully understood moment when a particle that had been spread across many possibilities suddenly chose one. Quantum measurement was the one place in physics where determinism broke down in a clean, mathematically respectable way. If consciousness needed a piece of physics that was not algorithmic, quantum measurement was the only candidate. So Penrose argued that consciousness must, somehow, be tied to quantum mechanics. He didn't say where in the brain. He didn't say how. He didn't have a mechanism. He just had an argument by elimination. The brain does non-computable things. The only known non-computable physics is quantum collapse. Therefore the brain must somehow be using quantum collapse. The Emperor's New Mind was, for a few hundred pages, an enormous question mark. What happened next is the kind of thing that should not have happened. The book came out. It became a popular hit. It infuriated the artificial intelligence community, which had been built on the assumption that intelligence is computation and consciousness is intelligence under another name. It bewildered most of neuroscience, which had no idea what to do with a physicist who insisted that the secret to the mind lived in particle physics. And in a hospital in Tucson, Arizona, in a corner of a building where surgeons routinely switched off the consciousness of human beings using gases that nobody fully understood, an anesthesiologist named Stuart Hameroff read the book. Hameroff had been thinking about consciousness, quietly and almost privately, for almost 20 years. He had spent most of his career watching the lights go out and come back on inside other people's heads. He had a hunch, almost a private obsession, about a particular structure inside neurons that he thought might be the place where consciousness lived. The structure was called the microtubule. It was small. It was elegant. It was almost everywhere. And it was, in 1992, almost completely ignored by the people studying the brain. Hameroff wrote a letter to Penrose. The letter was the second event in a story that would last another 37 years. The first event was Penrose's book. The second event was a single anesthesiologist deciding that maybe, just maybe, the mathematician was looking for something that he had been looking at for 2 decades. What follows is the story of what happened when those two men found each other, and of the strange 40-year argument that grew out of their collaboration. It is also the story of the door that was slammed shut in 2000 by a single calculation that almost everyone accepted as final, and the way that door has been quietly, slowly, undeniably swinging back open over the last 15 years. By the end, you will know more than most working scientists do about a theory that says, in essence, that there is something happening inside your skull right now that the rest of the universe cannot explain. You may decide the theory is right. You may decide it is wrong. You will not be able to dismiss it. There is something it is like to be you, listening to this. 40 years of physics have not been able to explain why. Get comfortable. This is the part where we find out what those 40 years have produced. Part 2. The Anesthesiologist's Letter. Stuart Hameroff was born in 1947 in Buffalo, New York. He went to the University of Pittsburgh for medical school, finished a residency in anesthesiology, and ended up at the University of Arizona in Tucson, where he would spend almost his entire career. The job of an anesthesiologist is, on paper, to keep surgical patients unconscious, breathing, and pain-free, while a surgeon does something terrible to their body. The job in practice is stranger than that. Anesthesiologists are the people in a hospital who routinely, deliberately, dozens of times a week, switch off the conscious experience of another human being. They watch it leave, they watch it come back. And if they pay enough attention, after enough years, they start to wonder what it is they are switching off. Hameroff paid attention. By the late 1970s, he was already thinking, in a way that was not really part of his job, about what consciousness was and where in the brain it might be sitting. He was particularly interested in a question that should have been a routine part of medical training: but turned out not to be. Namely, why do general anaesthetics actually work? It seems like the kind of thing a doctor ought to know. The honest answer, then and now, is that nobody quite does. To understand why this is strange, you have to understand what general anaesthesia looks like as a chemical problem. The drugs we use to put surgical patients to sleep include some compounds with almost nothing in common. Ether, the original anaesthetic discovered in the 1840s, is a small organic molecule with 2 carbon atoms and an oxygen. Halothane, isoflurane, sevoflurane, the workhorses of modern operating rooms, are halogenated hydrocarbons with no obvious common structure. Propofol is an entirely different kind of organic molecule, oily and fast-acting. Nitrous oxide is 2 atoms of nitrogen and 1 of oxygen. Xenon, used in some specialized procedures, is a noble gas, an element so chemically inert that for decades it was considered incapable of forming compounds with anything. Argon and krypton, 2 other noble gases, also induce anesthesia in animal models when delivered at high enough pressure. A receptor-based pharmacology, which is how most drugs work, would predict that this list could not possibly all be doing the same thing. Receptors are picky. They are shaped to recognize specific molecular structures. The lock and key model that has dominated drug discovery for a century says that if you change the shape of the key, you should not be able to open the same lock. And yet here is a chemical zoo of completely different molecular shapes that all, somehow, open the same lock, the lock that switches consciousness off. For more than 100 years, anesthesiology has known about a strange empirical regularity that hints at the answer. In 1899, a German pharmacologist named Hans Horst Meyer noticed that the potency of an anesthetic, across the whole chemical zoo, correlated almost perfectly with how soluble that compound was in olive oil. The more lipid-soluble, the lower the dose required to put an animal under. In 1901, an English biologist named Charles Ernest Overton, working independently, found the same thing. The Meyer-Overton correlation, as it came to be known, has held up for 120 years. It is one of the most reliable facts in clinical pharmacology, and it is, in a deep sense, an indictment of every receptor-based explanation that has been proposed for anesthesia. Receptors don't care about lipid solubility. Membranes do. The strong inference from the Meyer-Overton correlation is that anesthetics, despite their chemical differences, are all doing something inside the lipid membranes of brain cells. They dissolve into the membranes. They perturb something there. And the thing they perturb is, somehow, the thing that consciousness depends on. The question for the last 100 years has been, what is the thing? Hameroff had a candidate. He thought the thing was the microtubule. To see why he thought that, you have to know what a microtubule actually looks like. A microtubule is a hollow cylindrical lattice, built out of a protein called tubulin. The tubes are tiny, about 25 nanometers across on the outside, with an inner cavity about 15 nanometers wide. For comparison, that's a few hundred times narrower than a typical bacterium. Each microtubule is made by stacking up pairs of tubulin molecules, alpha-tubulin paired with beta-tubulin to form a dimer, into 13 parallel strands called protofilaments, arranged in a helical lattice along the length of the tube. The arrangement is so regular that microtubules look, under an electron microscope, like minuscule pieces of architectural ironwork. Microtubules are not unique to brain cells. Every eukaryotic cell uses them. They form the mitotic spindle that pulls chromosomes apart during cell division. They are tracks along which molecular motors carry cargo around the cell. They give cells their shape. Without them, eukaryotic life would not work. But neurons are unusually full of microtubules. A single pyramidal neuron in the cerebral cortex contains something on the order of 10 million tubulin dimers, packed into dense bundles inside the dendrites and the axon. And tubulin has a property that not many proteins share. It has an enormous electric dipole moment, about 1700 Debye units per dimer, which is gigantic by molecular standards. Each tubulin dimer is, in effect, a tiny electrical switch that can flip between two orientations. A microtubule, made of thousands of these switches arranged in a regular lattice, is, from a certain angle, a circuit. That was Hameroff's idea. He thought the cytoskeleton was not just structural scaffolding. He thought it was a hidden computational substrate inside every neuron, a lattice of tiny switches that could, in principle, store and process information at a scale the rest of neuroscience was ignoring. He had been making versions of this argument since the late 1970s, mostly to small audiences who politely changed the subject afterward. When Hameroff read The Emperor's New Mind in 1992, something clicked. Penrose was saying that consciousness needed a piece of physics that no classical computer could replicate. Hameroff already had a structure inside every neuron that nobody else thought was doing anything important. And he had a suspicion, from the anesthesia data, that consciousness lived in the lipid membranes near these structures. What if the microtubules were the place where Penrose's non-computable physics actually happened? What if the lights that anesthetics switched off were the quantum lights inside the tubulin lattice? He wrote to Penrose. The letter was short. It said, "In essence, I think I have your missing biology. Would you like to talk?" Penrose said yes. For most of the next 3 years, they corresponded and met whenever they could. Penrose, who had no medical training, asked Hameroff to walk him through what was known about microtubules, their structure, their dynamics, their role in anesthesia. Hameroff, who had no training in mathematical physics, asked Penrose to walk him through what was known about quantum measurement and about the specific gravitational mechanism Penrose had been developing as a possible explanation for wave function collapse. They wrote together. They argued. By 1993, they had a working draft of a joint theory. By 1996, the theory had a name, a paper in the journal Mathematics and Computers in Simulation, and a small but very determined community of curious outsiders watching to see what would happen next. They called it orchestrated objective reduction. They called it ORCOR for short. And the next part of this story is the part where the theory tells you, in clean physics-grade terms, what it actually claims is happening inside your head 40 times every second while you read these words. Part 3. Orchestrated Objective Reduction. Here is what Penrose and Hameroff worked out together. Each piece of the picture they constructed has been argued about, defended, attacked, and revised over the last 30 years. But the core proposal has stayed remarkably stable, and it is best understood as a single coherent claim. So let me give it to you in one breath. Inside every neuron in your brain, packed into the dendrites and the axons, there are millions of microtubules. Inside each microtubule, the tubulin dimers in the lattice are not just structural units, they are quantum mechanical systems. Each dimer has an electronic state that, under the right conditions, can exist in a superposition of two different configurations, two different orientations of the electric dipole, at the same time. The hollow interior of the tube, lined with structured water molecules that the cell carefully maintains, acts as a shelter for these superpositions, protecting them from the thermal noise of the surrounding cytoplasm. Across the lattice, many tubulin dimers can enter coupled superpositions, sharing quantum information across distances that are large by molecular standards. And across many microtubules in many neurons, the lattice acts like a coupled network of these quantum subsystems, a kind of biological quantum computer running underneath the classical neural network everybody else has been studying. Then, every 25 milliseconds or so, 40 times every second, something happens. The superposition becomes too large to sustain. The mass-energy difference between the two superposed states becomes big enough that, on Penrose's interpretation of gravity, space-time itself can no longer hold both versions in parallel. The superposition collapses. It chooses. The choice is not random. It is not determined by any classical algorithm. It is determined, in some way Penrose argues we do not yet have a complete physics for, by the geometry of space-time, by the structure of the universe at its deepest level. This moment of choosing, this orchestrated objective reduction, is, in their picture, a moment of conscious experience. That is the theory. That is what they are saying happens inside your head. 40 times every second, something is choosing to be you. The choice is not made by a neuron. It is not made by a chemical. It is made by reality itself, in the only place we know of where reality makes choices that no classical computer could predict in advance. Let me say that again, because it is the kind of claim that slides off the surface of the mind on first contact. Penrose and Hameroff are saying that consciousness is not a property of the brain in the way that digestion is a property of the gut. Consciousness, in this picture, is what the universe does when it commits to one outcome from a quantum superposition. The brain is the place this happens densely enough, and in a structured enough way, to produce the unbroken stream of experience you call your life. Everywhere else in the universe, this same thing is happening. A photon hitting a detector in a laboratory, a neutron decaying inside a dying star, a polarized electron arriving at a Stern-Gerlach magnet. But those events happen in isolation, scattered, unconnected. They are weather. Inside your brain, the same events are arranged in a lattice, orchestrated, woven into something coherent. They are music. This is not a small claim. It is one of the largest claims any physical theory has ever made about what minds are. And it has a specific number attached to it that makes it falsifiable in principle. Penrose's calculation says that the time it takes for a superposition of a given mass distribution to collapse is roughly Planck's constant divided by the gravitational self-energy of the difference between the two superposed states. For a tubulin scale mass distribution, the kind of superposition OR proposes inside a microtubule, the calculation gives a collapse time of about 25 to 40 milliseconds. 25 to 40 milliseconds. That number is not just any number. 40 milliseconds is the period of a 40 Hz oscillation, and 40 Hz is, suspiciously, the dominant frequency of the so-called gamma rhythm in the cortex, the brainwave that, since the 1990s, neuroscientists have associated with the binding of distributed cortical activity into unified conscious experience. Francis Crick and Christoph Koch, in a famous paper in 1990, proposed that gamma synchronization was the neural signature of consciousness itself. Other neuroscientists, including Wolfsinger in Germany, found the same pattern. The 40 Hz rhythm has been a candidate signature of conscious binding for more than 30 years, on entirely classical grounds. And here was Penrose, working from a completely different direction, from the gravitational self-energy of a microtubule-scale mass superposition, arriving at the same 40 Hz interval. Either it is a coincidence, or it is a fingerprint. The proposal is precise. It says where in the brain consciousness is happening, inside microtubules. It says what kind of physical event consciousness is, a gravitationally induced wave function collapse. It says how often consciousness updates, about 40 times a second. It says what the role of the rest of the neuron is, to orchestrate the microtubule-level quantum events into a coherent stream, and it makes specific empirical predictions about how anesthesia should work, about what should happen if you change the isotope of an anesthetic gas, about what should be measurable inside isolated microtubules under the right conditions. Every one of those predictions will, over the next 30 years, become a small front in a much larger argument. I want you to feel, for a moment, what this picture is asking you to hold. Right now, as these words enter your ears, somewhere inside your skull, millions of microtubules are humming with coupled quantum states. 40 times a second, the coupled states are too large for space-time to keep in superposition, and they collapse, together, in concert, orchestrated by the lattice, into a single configuration. Each collapse on this view is a moment of you. You're not a continuous stream. You're a rapid sequence of choices that the geometry of the universe is making at the scale of your brain. The continuity you feel is an illusion of pacing. If this is right, the boundary between you and the rest of the universe is much thinner than common sense suggests. The 40 Hz rhythm is not just a brainwave. It is the rate at which reality is committing to a particular version of you. The act of attention, The thing you're doing right now to follow these words is not just neurons firing, it is reality at the scale of your brain, choosing 40 times a second to keep being yours. 40 times a second, something is choosing to be you. That is the sentence the theory leaves you with. We're going to come back to it. We're going to come back to it twice. The first time will be in the middle of this story, when an experiment finally reaches inside a microtubule and the lattice rings. The second time will be at the very end, when the only experiment that matters, the one running inside your head right now, is the only piece of evidence left. But before any of that, the theory has to survive the next 20 years. And in the year 2000, a young physicist at the University of Pennsylvania is about to publish a single calculation that almost everyone in physics will accept as the final word. Almost everyone. The next part of this story is the door slamming shut. There is a peculiar honesty in the precision of the auteur proposal that I want to make sure you do not miss. Almost all theories of consciousness, on every side of the debate, are deliberately vague. They have to be. The phenomenon is hard. The evidence is fragmentary. The temptation for anyone trying to talk seriously about consciousness is to stay at a level of abstraction where you cannot be obviously wrong. You say things like, consciousness emerges from the integration of information. You say things like, consciousness is a global broadcast. You say things like, consciousness is what it is like to be a system that represents itself. These are all interesting moves, but they are deliberately structured to resist being falsified. They do not commit. They cannot, in the technical sense, be put to a clean experimental test. Auteur is the opposite. Auteur commits. It says, here is the structure inside the cell where it happens, microtubules. Here is the molecule that carries the relevant quantum mechanical property, tubulin. Here is the time scale, 25 to 40 milliseconds. Here is the underlying physics, gravity-induced wave function collapse on the Penrose interpretation. Here is the prediction that should distinguish it from classical theories, that anesthetics should perturb the quantum state of the tubulin lattice, that microtubules should support coherent oscillations at the right frequencies, that isotopic substitution of anesthetic gases should produce dose shifts that classical pharmacology forbids. These commitments are the reason the theory has been so easy to attack and so hard to kill. They give experimentalists something to look for. Every time experimentalists look, the theory either passes the test or fails it. After 30 years of looking, more of the predictions have come in on the theory's side than anyone in 2000 would have expected. You can take that as a reason to believe auteur, or you can take it as a reason to be suspicious of how predictive it has turned out to be. There are, in the history of science, theories that made good predictions and turned out to be wrong for other reasons. The point is that the theory is not vague. It is specific in a way that lets the experiments do their work. That specificity is its strongest feature, and depending on how the experiments go, will be either the source of its eventual vindication or the source of its eventual final defeat. Part 4. The decoherence calculation. In the year 2000, a 33-year-old Swedish-American cosmologist at the University of Pennsylvania published a paper in the journal Physical Review E. The cosmologist's name was Max Tegmark. He would go on, in the years after, to become famous for other things, for the multiverse, for ambitious books about parallel universes, for a kind of fearless willingness to take strange ideas seriously and see where they led. But in 2000, Tegmark was a junior physicist with a calculation he thought needed to be done. The paper was called Importance of Quantum Decoherence in Brain Processes. It was 7 pages long. It would, for almost 2 decades, be treated as the final word on whether auteur could possibly be right. To understand what Tegmark did, you have to understand a concept that has been at the heart of quantum mechanics since the late 1970s, when physicists like Heinz-Dieter Zeh and Wojciech Zurek first put it on solid mathematical footing. The concept is called decoherence. It is the answer, or at least a large part of the answer, to one of the oldest puzzles in physics. Why doesn't the everyday world look quantum? Quantum mechanics says that particles can exist in superpositions. An electron can be in two places at once. A photon can pass through two slits simultaneously. A radioactive atom can be both decayed and undecayed before you measure it. The math works. The experiments confirm it, over and over, with greater precision every decade. But you do not see superpositions in your kitchen. Your coffee cup is in one place. Your hand is on the doorknob, not at the table. The macroscopic world looks classical. Why? The decoherence answer is that quantum superpositions are extraordinarily fragile. The moment a quantum system interacts with its environment, collides with a stray photon, bumps into a passing air molecule, exchanges any energy at all with the warm world around it, the superposition leaks information into the environment, and once the information is leaked, the superposition behaves, for all practical purposes, like a classical probability distribution. The two branches of the superposition stop being able to interfere with each other. The quantum strangeness is suppressed. The system looks like one or the other of its possibilities, not both. The decoherence timescale is the rough answer to how long a superposition can survive in a given environment before this leakage finishes. For an electron in deep space, the decoherence timescale is enormous, minutes, hours, longer. For an electron in a perfectly engineered laboratory dilution refrigerator at thousandths of a degree above absolute zero, it can still be a respectable fraction of a second. For an electron at room temperature in air, it is staggeringly short, femtoseconds, sometimes attoseconds. For a macroscopic object like a coffee cup, the decoherence time is so short that it is, for any practical purpose, instantaneous. That is why your coffee cup does not look like a quantum object. It has been continuously measured by every photon, every air molecule, every gravitational interaction with the room since the moment it was made. Tegmark asked the obvious question. The brain is not a dilution refrigerator. The brain is a warm, wet, salty, electrically active organ at 37 degrees Celsius, packed with ions, water molecules, dissolved proteins, and constant thermal noise. If you wanted to design an environment that was hostile to quantum coherence, you could not do much better than the inside of a living head. How long, on average, could a superposition of the kind OR required actually survive there? He did the calculation. He treated the tubulin scale mass distribution OR proposed as a model superposition. He embedded it in the physiological saline of neural cytoplasm at body temperature. He worked through the thermal collisions with surrounding water molecules and ions. He calculated, with what most physicists would consider standard methods, the decoherence timescale. His answer was about 10 to the minus 13 seconds. That is 1/10 trillionth of a second. The number is so small that it is hard to feel in any meaningful way. Let me put it another way. A conscious thought takes somewhere between 1 and 10 milliseconds to register, 10 to the minus 3 or 10 to the minus 2 seconds. Tegmark's decoherence number was about 10 orders of magnitude, 10 billion times, faster than a conscious moment. By the time the brain could even begin to use a quantum state for anything resembling cognition, the state would have been gone for 10 billion times the duration of a thought. The implication, in Tegmark's reading, was final. OR was not just wrong, it was wrong by 10 orders of magnitude. The decoherence time of a tubulin-scale superposition in a warm-wet brain was so far below the timescale of consciousness that you could not even talk about the gap as a quantitative disagreement. It was a categorical refusal. Biology at body temperature was simply not, on this calculation, the kind of place where quantum coherence could persist long enough to matter. The reaction was swift. Within months, the consciousness research community, the physics community, and most of philosophy of mind had absorbed Tegmark's number as the death certificate for OR. The theory was treated in graduate courses and at conferences as a cautionary tale about what happens when a brilliant mathematician strays out of his discipline and starts speculating about biology. Penrose and Hameroff defended their proposal in print. They wrote response papers, Hagen, Hameroff and Tuzinski in 2002, arguing that Tegmark had used the wrong superposition geometry, neglected screening effects from ordered water at protein surfaces, and underestimated the symmetry-protected coherence available in the tubulin lattice. The exchange continued in the technical literature for years, but the wider community had moved on. The verdict, for almost everyone watching from the outside, was settled. For roughly 2 decades, Ochoa lived in the wilderness. It was the theory you brought up at consciousness studies conferences to provoke a laugh. It was the theory that philosophy graduate students learned about so they could explain, with the right knowing tone, why it was wrong. Hameroff continued to give talks at the Tour de Science of Consciousness conference series he had helped found in Tucson. Penrose continued to write books, Shadows of the Mind in 1994, The Road to Reality in 2004, Fashion, Faith and Fantasy in The New Physics of the Universe in 2016. And in each of them, he revisited Ochoa briefly, defended it briefly, and pressed on with his other work. The theory was, in the language of the trade, a fringe view held by 2 prominent eccentrics. Almost nobody was working on it. The field had a verdict, and the verdict was no. I want you to sit for a moment in the silence of those 2 decades. Imagine being Stuart Hameroff in 2004, giving a talk at a consciousness conference, looking out at an audience of polite skeptics. You have a theory you believe is right. The man you developed it with has a Nobel quality reputation. You have specific predictions about anesthesia, about microtubule dynamics, about gamma band binding. You have detailed responses to the decoherence critique, and you have nothing, no replication, no controlled experiment, no smoking gun observation that you can put on the table and say, look, this is the thing the theory said would be there. It is a particular kind of professional loneliness, that. The kind that requires a real conviction to survive. And in the early 2000s, almost no working scientist would have been willing to bet a career on the conviction that the verdict was going to be reopened. The lights went out on Ochoa. They were out for almost 20 years, and then a green sulfur bacterium sitting in a beaker on a bench at Berkeley was hit by a photon. And the photon did not do what classical chemistry said it should do. There is a particular detail about Tegmark's 2000 paper that is worth pausing on, because it tells you something about how the verdict on Ochoa got locked in for as long as it did. The paper was not a long, careful, exhaustive study. It was 7 pages. It used standard methods. It applied those methods to a model of the relevant biological structure that was, in retrospect, oversimplified. A model that treated the microtubule as a generic protein cluster sitting in a generic physiological saline, with no special architectural features and no protective shielding. Tegmark himself in the paper acknowledged that the calculation was approximate. He framed it as a useful order of magnitude estimate, not as a definitive proof. But the field treated it as definitive, because the order of magnitude estimate was so far off from what Ochoa required that even a generous interpretation could not save the theory. This is how scientific consensus often works on questions that are far from anyone's daily research interests. The community does not, in general, have time to scrutinize every paper carefully. When a respectable physicist publishes a calculation showing that a strange theory is wrong by 10 orders of magnitude, the calculation gets accepted as a working approximation of the truth, and the strange theory gets shelved. The shelving happens not because the community has carefully evaluated the alternative, but because the cost of taking the alternative seriously is high and the apparent return is low. For most working researchers in 2001, 2002, 2003, Ochoa was not a question they needed to think about. Tegmark had done the calculation. The calculation said no, move on. What changed, slowly, was that the calculation stopped being trusted. Not by everyone. The calculation is still cited, still defended in some quarters, still considered a serious objection. But the methodological assumptions behind it, the treatment of biological tissue as generic, the absence of structure-specific shielding, the absence of evolutionary refinement of the relevant geometries, have all weakened under the weight of quantum biology results. A calculation whose key assumption has been undermined is no longer a definitive verdict. It is, at best, a starting point. That is where Tegmark's number sits now. It is a starting point, not a verdict. The field is doing the work of figuring out what the actual answer is, with structure-specific data, and that work is not done. I want you to feel the weight of how long the shelving lasted. 20 years. 20 years of graduate students being told the theory was dead. 20 years of conferences where the theory was the punchline of a polite joke. 20 years of Hameroff at the Tour de Science of Consciousness meetings he had helped create, giving talks in mostly empty rooms. The cost of being a defender of Auture during those 20 years was not just professional, it was social, intellectual, daily. You had to spend 20 years standing in a position that the people you respected most considered indefensible. Most people would not have done it. Most people would have moved on, said in private that they used to find the theory interesting, taken up something less embarrassing. Hameroff did not move on. He kept giving the talks, he kept publishing the responses, he kept developing the theory in collaboration with whoever was willing to work on it. Penrose did not move on either. He kept writing the books, he kept defending the calculation, he kept telling interviewers, when the question came up, that he still thought Auture was the most promising approach to a hard problem nobody else was solving. They were, both of them, by any reasonable measure, professionally stubborn to a degree that bordered on perverse. And as it turned out, the perverse stubbornness was, eventually, what kept the theory alive long enough for the experimental tools to catch up. This is one of the recurring patterns in the history of science. The patterns of theories that are killed prematurely and then rehabilitated by experimental progress that nobody predicted. Continental drift was killed by Lord Kelvin in the 1860s and rehabilitated by plate tectonics in the 1960s. The germ theory of disease was killed repeatedly by the medical establishment of the 18th century and only rehabilitated in the 19th by Pasteur and Koch. Heliocentrism was killed by Aristotelian physics for 1,000 years before Galileo's telescope made it impossible to deny. The pattern is consistent enough that you should not assume, when a theory is dismissed, that it is gone for good. You should ask instead whether the dismissal was based on the kind of evidence that can be reopened by future experimental work. If it was, the theory is not dead. It is dormant. Auture is dormant no more. Part 5. The Leaf. In April of 2007, the journal Nature published a paper from the laboratory of Graham Fleming at the University of California, Berkeley. The first author was a young physical chemist named Gregory Engel. The paper was titled, in the dry technical voice of high-impact scientific publishing, Evidence for Wave-like Energy Transfer Through Quantum Coherence in Photosynthetic Systems. It was, on the surface, a paper about how plants capture sunlight. Underneath that surface, it was the first crack in the wall that Max Tegmark had built around the brain. To understand what Engel and Fleming had done, you need to know what photosynthesis looks like as a quantum problem. Every leaf on every plant on this planet is, at the molecular level, a forest of light-harvesting protein complexes embedded in chloroplast membranes. When a photon of sunlight strikes a chlorophyll molecule in one of these complexes, it deposits its energy into the chlorophyll's electrons. The energy has to be transferred very quickly to a specific molecular destination called the reaction center, where it can be used to drive the chemistry of converting carbon dioxide and water into sugar. If the energy gets lost on the way, if it sits around long enough to dissipate as heat, the photon is wasted. Photosynthesis would be inefficient. Life on Earth would have a much harder time. But photosynthesis is not inefficient. It is one of the most efficient energy transfer processes ever measured. Under the right conditions, light-harvesting complexes deliver energy to the reaction center with quantum yields above 95%. Almost no energy is lost. And for decades, this efficiency was an open puzzle, because classical models of energy transfer, models that treated the energy as hopping randomly from one chlorophyll to the next, like a drunkard's walk through a forest, could not reproduce it. random hopping is not how you achieve 95% efficiency. Engel and Fleming used a technique called two-dimensional electronic spectroscopy. The basic idea, which had been developed over the previous decade by Fleming and others, is to hit a sample with a precisely timed sequence of laser pulses and watch how the resulting electronic excitations evolve over time. By analysing the patterns of how energy flows between different molecular sites, you can tell whether the energy is moving by classical hopping or by some kind of quantum coherent process. A process in which the energy is, in effect, in superposition across multiple molecular sites at once. They studied a specific protein complex called the Fenner-Matthews-Olsen complex, or FMO. The FMO complex is found in a particular kind of bacterium called Chlorobium tepidum, a green sulfur bacterium that lives in some of the strangest environments on Earth: hot springs, deep ocean vents, the lightless margins of geothermal lakes. The FMO complex is small, well studied, and well suited to the experimental method. They cooled their samples to 77 Kelvin, did the spectroscopy, and looked at the result. The result was that the energy was not hopping. The energy was demonstrably in a coherent quantum superposition, spread across multiple chlorophyll sites in the complex at the same time, and the superposition was not collapsing in femtoseconds. It was lasting for hundreds of femtoseconds, 660 femtoseconds in their initial measurement, long enough for the energy to, in effect, sample multiple possible pathways through the complex and find the most efficient one. This was, mathematically and physically, the answer to the photosynthesis efficiency puzzle. The energy was using quantum superposition to do something like a parallel search of possible routes, and only collapsing into one route once a sufficiently efficient path had been found. The leaf was, in a meaningful and measurable sense, exploiting quantum mechanics to harvest light. And it was doing it in warm, wet biological tissue. Not at thousandths of a degree above absolute zero, not in vacuum, not in a laboratory dilution refrigerator, in the kind of place where, according to the decoherence consensus, quantum coherence simply was not supposed to be possible. 2 years later, in 2010, a group led by Greg Engel, by then at the University of Chicago, published a follow-up paper in Proceedings of the National Academy of Sciences. They repeated the experiment but at room temperature, 300 Kelvin, body temperature roughly, and the coherence was still there, shorter, about 150 femtoseconds give or take, but still measurable, still real, still using quantum mechanics to find efficient pathways through the protein complex. The implications rippled outward through biology with surprising speed. The blanket statement that had killed Orch-Orr, the statement that warm, wet biological tissue could not host meaningful quantum coherence, was not, in fact, true. It had been said with great confidence by people who had not actually looked. Now somebody had looked, and the consensus was wrong. Quantum coherence did persist in biological systems at biological temperatures, not for very long, not for full seconds or full milliseconds, but long enough, in at least one case, to do important biological work. This is the science we're watching the implications of, you watching it from your bed or your kitchen or wherever you are right now, in the soft hours of the night. Every leaf you have ever seen has been doing this. Every blade of grass on every lawn you have ever walked across has been running a quantum mechanical search for efficient light capture, 3.5 billion years of evolutionary refinement before any human physicist arrived to be surprised by it. The leaf knew. The leaf had been knowing the whole time. If the leaf had been doing this, what else had biology figured out? The list grew quickly. Within a few years, researchers had identified, with varying degrees of confidence, several other places where quantum mechanics seems to play a load-bearing role in living systems. The most striking was the navigation system of migratory birds. Klaus Schulten, a theoretical biophysicist, had proposed back in 1978 that birds might sense the Earth's magnetic field using a quantum mechanical mechanism, a so-called radical pair mechanism, in which two electrons whose spins are quantum mechanically entangled act as a tiny compass, with the entanglement modulated by the local magnetic field. For decades, the proposal was theoretical. Then, in 2000, Thorsten Ritz, working with Schulten and others, showed behavioural evidence consistent with the mechanism in European robins. Over the following decade, the radical pair model became the leading explanation for avian magnetoreception, with the relevant biochemistry traced to a protein called cryptochrome in the bird's retina. A bird, when it migrates, is reading the Earth's magnetic field through a quantum entanglement in two of its own eye proteins. The bird sees the field. There was more. Enzyme catalysis turned out, in several well-studied cases, to depend on quantum tunneling, the process by which a particle can pass through an energy barrier that, classically, it should not have enough energy to climb. The work of Judith Klinman and others, starting in the late 1990s, established that protein-mediated proton tunneling is essential to the function of enzymes like alcohol dehydrogenase. There was a contested but persistent claim, advanced by Luca Torria starting in 1996, that the sense of smell depends on inelastic electron tunneling in odorant receptors, a quantum signature that would explain why molecules with very different shapes but similar vibrational frequencies can smell alike. The Turing proposal remains controversial. Some replications have failed, others have succeeded. The field has not fully closed it. But the existence of the debate in serious peer-reviewed journals was itself a measure of how far the field had moved. By the mid-2010s, the term quantum biology had its own conferences, its own textbooks, its own funded research programs. The blanket statement that had ended Orkor's first life was not just contested, it was, in a quiet, decade-by-decade way, retired. The field stopped pretending that warm-wet biology was a desert for quantum effects. It had to. The evidence had piled up. Nobody, in any of these papers, claimed to have vindicated Orkor. None of these experiments touched microtubules. None of them addressed consciousness. None of them, individually, was a smoking gun. But collectively, they did something that mattered. They removed the categorical objection. They moved Or from is impossible to is not yet supported. That is a smaller sounding distinction than it really is. In science, the difference between impossible and not yet supported is roughly the difference between dead and alive. Quietly, without fanfare, the door that Max Tegmark had slammed shut in 2000 was being unlatched. Nobody was opening it yet, but the lock had broken. Part 6. The Widening Crack. You have to imagine the 2010s the way they actually felt to the people inside the consciousness research community, because it was not a single dramatic moment. There was no announcement, no press conference, no headline that said the decoherence consensus had collapsed. There was instead a slow accumulation of small papers, modest conference talks, careful experimental reports, each one, on its own, a curiosity, and all of them together, by about 2015, an unmistakable trend. The trend was that biology kept doing things classical physics did not predict. The radical pair magnetic compass in birds went from speculative to mainstream. The room temperature quantum coherence in photosynthesis was replicated in multiple light harvesting complexes from multiple organisms, eventually including higher plants and not just bacteria. The proton tunneling story expanded from alcohol dehydrogenase to a whole family of enzymes whose reaction rates simply could not be explained without quantum tunneling contributing to the rate-limiting step. Theoretical work by groups in Oxford and Singapore and Munich and Cambridge started to make sharper predictions about what kinds of biological structures could and could not host useful quantum coherence, and the predicted structures were more numerous and more humble than the early skeptics had imagined. Meanwhile, in the corner of the field that still cared about Orkor, something specific was happening with the microtubule. A handful of laboratories around the world had begun to do detailed measurements of microtubule physics that, for the first time, were sensitive enough to test some of Orchoa's predictions directly. The most aggressive of these efforts came out of Tsukuba, Japan, from the laboratory of a quantum physicist named Anirban Bandyopadhyay, at the National Institute for Material Science. Bandyopadhyay was, depending on whom you asked, either one of the most interesting experimentalists working in biophysics or one of the most controversial. His group had developed techniques for probing the electrical properties of single isolated microtubules using nanoelectrodes, tiny conducting tips that could touch a single tubule and measure its response to applied voltages and currents. Starting around 2013, he began publishing results that, if real, were remarkable. He reported that microtubules, when probed with the right kind of electrical signals, exhibited sharp resonant oscillations across an extraordinary range of frequencies, from megahertz through gigahertz, all the way up into the terahertz range. The resonances were sharp, they were stable, they were reproducible inside his lab, and they had the structure that you would expect from a coherent oscillator system, something more like a tuned circuit than a passive piece of biological scaffolding. If you were a believer in Orshaw, the Bandyopadhyay measurements were the first time anyone had reached inside the actual structure the theory pointed at and found it ringing. If you were a skeptic, the measurements were possibly an artifact, the apparatus picking up its own resonances, the probe coupling to environmental electromagnetic noise, the data overinterpreted. Replication, by other groups using different equipment, was partial. Some confirming results appeared from other laboratories. Some contradicting results appeared as well. The Bandyopadhyay program is, even today, contested. It is not settled science. But it is also not nothing. It is the first generation of experimental measurements that genuinely tests, rather than dismisses, what Orshaw claims about the structure of microtubules. I want to slow down here for a moment, because the story is about to shift again, and I want you to feel the shape of the shift. By around 2015, the consciousness research community was in a strange position. The decoherent consensus that had killed Orshaw was no longer being defended with the same confidence. Quantum biology had become a respectable subfield. Specific structures inside neurons were being measured with techniques that approached the resolution Orshaw would require to be testable. None of this added up to vindication, but it added up to something that was no longer dismissal. And then, in the second half of the 2010s, the people who had been quietly working on the quantum biology end of the spectrum started thinking carefully about a specific molecule that sits at the center of the Orshaw proposal, the amino acid tryptophan. Tryptophan is one of the 20 standard amino acids that build all the proteins in your body. It is abundant in tubulin. It is also, structurally, an aromatic molecule with a particular kind of electronic structure that makes it interesting from a quantum optical perspective. Tryptophan absorbs ultraviolet light. Tryptophan fluoresces. And when many tryptophans are arranged in a structured network, when, for instance, they are stacked in regular geometric patterns inside a protein lattice, they can, in principle, exhibit a quantum optical phenomenon called superradiance. Superradiance was first predicted by the American physicist Robert Dicke in 1954. The basic idea is that when many emitters of the same kind are arranged closely enough together, their emissions are not independent. They become coupled. They share a single collective quantum state. And when the collective state decays, it does so much faster and much brighter than any individual emitter would. The cooperative emission produces a brief intense pulse, a coherent flash of light from a small ensemble of atoms or molecules behaving, briefly, as a single unified quantum system. If the tryptophans in tubulin were arranged in a structured enough way, and if the protein-protein contacts in the microtubule lattice happened to bring those tryptophans into the right geometric configuration, then microtubules might support superradiance. The cooperative quantum optical state would be a coherent multi-tryptophan superposition, exactly the kind of thing Orshaw needs in exactly the molecule Orshaw points at. It would be a specific falsifiable prediction. Either the superradiance was there or it wasn't. Either room temperature aqueous solution killed the cooperative state or it didn't. By 2023, several theoretical groups had worked out the relevant predictions in enough detail that an experimental group with the right tools could go look. The experimental group that went looking was at the University of Toronto. The first author of the resulting paper would be a young chemist named Travis Babcock. The senior author would be Greg Scholes, one of the most respected spectroscopists in quantum biology, a man whose lab had been doing rigorous measurements of biological quantum effects for over a decade. They had no particular axe to grind on Orkor. They were not Hameroff allies. They were not Tegmark partisans. They were a high-quality experimental group asking a specific question. In April of 2024, the result appeared in the Journal of Physical Chemistry B, and the result was that the tryptophans in tubulin do exhibit superradiance at room temperature in aqueous buffer. The lights, in that moment, did not come back on inside Orkor all at once, but somebody had quietly walked into the dark room, found the switch, and started turning it. The next part of this story is what happened when other groups, looking in slightly different directions, found other switches. There is a subtlety in this 2010 shift that I want to make sure you feel, because the standard popular telling of the quantum biology revolution leaves out the part that matters most for the consciousness debate. The standard telling is that quantum biology proved that warm-wet biology can host quantum coherence, and therefore Orkor has been vindicated. That is not quite right. What quantum biology actually showed is that warm-wet biology can host quantum coherence on the timescale of hundreds of femtoseconds. Hundreds of femtoseconds is a long time compared to Tegmark's 2000 decoherence estimate for tubulin, which was 10 to the minus 13 seconds, about 100 femtoseconds. So in one sense, the early quantum biology results closed a small fraction of the 10 order of magnitude gap Tegmark had identified. They did not close all of it. The gap between hundreds of femtoseconds and milliseconds is still many orders of magnitude. What quantum biology did do, more importantly than closing the gap, was undermine the methodology by which the gap had been estimated in the first place. Tegmark's calculation, and similar calculations by other physicists in the late 1990s and early 2000s, treated biological tissue as a generic, warm, noisy environment with no special structure. The calculations modelled the proteins as classical objects sitting in classical fluid, exchanging classical energy with classical surroundings. The conclusion that quantum coherence could not survive was a consequence of that modelling choice. What the quantum biology results showed is that the modelling choice is wrong. Biological proteins are not generic objects in generic fluid. They are evolved structures, 3.5 billion years old, with internal geometries that protect specific quantum states in ways generic calculations did not anticipate. The FMO complex shields its excitons. The cryptochrome protein in the robin's retina shields its radical pair. The enzymes that catalyze key reactions shield their tunneling protons. Biology has had a long time to figure out how to keep specific quantum states alive against the thermal odds. Once you accept that biology shields quantum states against generic decoherence calculations, the Tegmark estimate stops being a hard upper bound on Orkshaw's microtubule coherence times. It becomes, at best, a starting point. The actual upper bound depends on the specific structure of the microtubule, the specific arrangement of tubulin dimers, the specific role of structured water in the lumen, the specific contribution of tryptophan networks to cooperative quantum states. Those questions are not settled. But they are now the right questions, and those are the questions that the Bandyopadhyay measurements and the Babcock superradiance work and the West anesthetic isotope experiments are starting to give partial answers to. What you are watching in the 2010s and 2020s is the slow replacement of a generic decoherence argument with structure-specific experimental data. The generic argument was the basis for Orkshaw's 2-decade burial. The structure-specific data has, in the last few years, started to undo that burial. Whether the data eventually settles in favour of Orkshaw or against it is a question for the next decade. What is already clear is that the verdict cannot be reached by arithmetic alone. It has to be reached by going inside the actual structure and measuring what is there. That is, finally what people are doing. Part 7. Inside the tube. I want you to come down with me in your imagination through the scales. We're going to leave the cortex behind. We're going to enter a single neuron. We're going to find one microtubule in one of its dendrites, and we're going to step inside. Begin at the level you live at, the world of inches and meters, of rooms and bodies. From there, descend. The neuron you're about to enter is part of the prefrontal cortex of someone listening to a soft voice in the middle of the night. The cortex is, in cross-section, about 2.5 millimeters thick. The neuron is a pyramidal cell, named for the triangular shape of its body, about 20 micrometers across, which is roughly 1/50th of a millimeter. Its dendrites, the branching antennae that gather signals from thousands of other neurons, stretch out into the surrounding tissue like the bare limbs of a winter tree. Each branch is about 1 micrometer wide. We are descending through 6 orders of magnitude. We are leaving the world the body lives in. We are entering the world the cell lives in. Inside the dendrite, the cytoplasm is dense. Proteins, lipids, ribosomes, mitochondria, signaling molecules, water structured in layers around every solute. Running through the cytoplasm, oriented roughly along the length of the dendrite, are bundles of long, thin cylinders. These are the microtubules. Each one is 25 nanometers across, 25 billionths of a meter. That is about the diameter of 100 hydrogen atoms placed in a row. Microtubules are, by the standards of your everyday world, almost nothing. By the standards of the molecular world, they are large, deliberate, beautifully built structures. Step closer. Pick one microtubule. The wall of the tube is built out of pairs of proteins. Alpha-tubulin paired with beta-tubulin to form a dimer about 8 nanometers long. The dimers are stacked end-to-end into 13 parallel strands called protofilaments that run along the length of the tube. The protofilaments are arranged in a regular helical lattice. From the outside, the surface looks like a piece of architectural ironwork, a regular pattern of two-tone tiles, alpha next to beta, beta above alpha, repeating in a precise spiral. Each tile is a little more than 4 nanometers tall. There are millions of them in a single microtubule. Now go inside. The lumen, the hollow inner cavity of the tube, is 15 nanometers across. The walls rise around you like the inside of a chapel. You are alone in here, except for water. The water inside a microtubule is not the loose, free water of the cytoplasm outside. It is structured water, layers of water molecules whose orientations are partially organized by the geometry of the lattice walls. Some research, by groups around the world, has suggested that this structured water plays a specific role in the quantum physics Orshar proposes. It acts as a kind of shield, screening the interior from the thermal chaos of the surrounding ions and free water molecules, extending the timescale over which a quantum coherence can survive inside the tube. Look up. Above you, the lattice rises like the ribs of a cathedral. Every tubulin dimer in the wall is, at the level of its electronic structure, a tiny switch. Its dipole moment can point in one direction or another, 1700 debye units, which is, on the molecular scale, an enormous separation of charge. Each switch can, in the Orshar picture, be in one configuration or another, or in a quantum superposition of both at the same time. Across the lattice, neighbouring switches are coupled. A flip in one influences its neighbours. The wall is, in this picture, a coupled quantum system. Then there are the tryptophans. The tubulin dimers contain a number of tryptophan amino acids, 8 per dimer, arranged in specific positions within the protein's three-dimensional structure. When the dimers are stacked in the microtubule lattice, the tryptophans from neighbouring dimers come into specific geometric relationships with each other. They form networks, small clusters of tryptophans in close enough proximity to share excited electronic states. And these clusters, as the Babcock-Scholes work in 2024 demonstrated, can support superradiance. They can act, briefly, as single collective quantum emitters of ultraviolet light. Now multiply this picture. One pyramidal neuron contains, on average, something on the order of 10 million tubulin dimers, packed into thousands of microtubules running through its dendrites and axon. 86 billion neurons in the cortex, each one with this same hidden architecture. The total tubulin in your brain is, in mass terms, larger than the total mass of any neurotransmitter, larger than the total mass of any single classical signaling molecule. The cytoskeleton is, by mass alone, a major component of who you are, and in the Auchor picture, this entire architecture is, at any given moment, in a coupled quantum state. The tubulin switches across many microtubules are in shared superpositions. The tryptophan networks are emitting and absorbing coherent ultraviolet photons. The structured water is shielding the coherent state from the thermal storm outside. And 40 times every second, the whole system reaches a threshold where the gravitational self-energy of the superposed mass distributions becomes too large for space-time to maintain, and it collapses. One configuration is chosen. The choice is not made by neurons. The choice is made, in Penrose's interpretation, by the geometry of the universe at the smallest possible scale. This is the picture. Stand inside it for a moment, up the cathedral walls, through the structured water, out across the coupled lattice. 40 times a second, something is choosing to be you. That is the sentence I left at the end of part 3. It is the sentence I am returning to now. I gave it to you the first time as theory, as a thing Penrose's calculation said might be happening, if the calculation was right. I am giving it to you the second time after a chapter in which experimentalists have started reaching inside the actual structure with actual instruments, and the structure has, in some cases, started to ring back. The sentence has not been proved, but it has been measured against. The lattice has been touched. The tryptophans have been seen to emit cooperatively. The microtubules have been seen to resonate. The shape of what is happening inside the tube is no longer entirely hypothetical. 40 times a second, something is choosing to be you. Hold that. We will come back to it once more at the end, when the only experiment left is the one running in your head right now. Part 8. Tryptophan. The Babcock-Scholes paper, when it appeared in April of 2024, did not arrive with the kind of fanfare that the discovery of room-temperature quantum coherence in microtubule proteins might have warranted in a different universe. Most working consciousness researchers did not see it. Most working neuroscientists did not hear about it. It was a paper in a respectable but specialized journal, written in the careful technical language of physical chemistry, full of spectroscopic detail that required a serious background to evaluate. And like most papers, it landed quietly, was cited slowly, and waited for the field to catch up to what it had reported. But the people who were paying attention recognized what it meant. The Babcock paper was, for the first time, a clean experimental demonstration that a specific quantum coherent effect, superradiance, survives at room temperature, in aqueous buffer, in the exact molecule that Auchor claims is doing the central work. It was not a demonstration that microtubules are conscious. It was not a demonstration that the brain is a quantum computer. It was a demonstration that the lattice geometry of tubulin, which had been described in atomic detail for decades, supports a specific cooperative quantum optical state that classical molecular dynamics models cannot produce. For a theory that had spent 20 years being told it was forbidden by the laws of decoherence, this was significant. It was the same kind of significance that the 2007 Fleming paper had for the broader field of quantum biology. It was a result that did not, on its own, prove a larger claim, but that removed a categorical objection. After 2007, you could no longer say that warm-wet biology cannot host any quantum coherence. After 2024, you could no longer say that tubulin specifically cannot host the kind of coherence Auchor requires. What made the Babcock paper especially interesting was the room it opened up for further experiments. Superradiance, as a quantum optical phenomenon, is well understood from decades of work on atomic and molecular systems. It has specific signatures: the timescale of the cooperative emission, the intensity of the emitted pulse, the way the emission scales with the number of coupled emitters. If you wanted to test whether the Babcock result was real, or whether it was an artifact of the specific experimental setup, you had clear predictions to check. Different geometries of tryptophan clusters should produce different emission timescales. Damaging the lattice should disrupt the cooperative state. Specific small molecules that bind in the right places, and the relevant question is whether any of the general anesthetics happen to bind in those places, should suppress the superradiance. That last possibility, that anesthetics might suppress the cooperative quantum state in tubulin, sat at the centre of a separate experimental program that was unfolding in parallel at a small college in Massachusetts. The college was Wellesley. The principal investigator was a neuroscientist named Mike Wiest. He had been thinking for a while about a question that Penrose and Hameroff had raised years before, but that nobody had quite known how to test: whether the mechanism of general anesthesia involves a perturbation of quantum mechanical states inside the protein targets, rather than a classical receptor-binding interaction. The way to test this is through what physical chemists call an isotope effect. Classical pharmacology says that the activity of a drug depends on its chemical structure: the arrangement of atoms, the shape of the molecule, the electrostatic surface that interacts with the protein target. Classical pharmacology does not care in any meaningful way about the isotopic composition of the drug. Replacing carbon-12 with carbon-13, or hydrogen with deuterium, changes only the nuclear mass, and nuclear mass, in classical chemistry, is irrelevant. But in quantum mechanics, nuclear mass matters. The mass of a nucleus affects the rate at which a particle can tunnel through an energy barrier, the frequency of certain vibrational modes, the structure of quantum coherent states in coupled systems. If anesthetics work through quantum mechanical perturbation of their targets, then changing the isotopic composition of the anesthetic should change the potency, in a way that classical pharmacology forbids. The theoretical proposal for an anesthetic isotope effect was old. It had been advanced in the early 2010s by Luca Turin and Andrew Horsfield. They predicted that for certain anesthetics, isotopic substitution would shift the dose required to induce unconsciousness. The prediction was specific. It was also, until the late 2010s, untested in any clean experimental design. Wiest's group, working with collaborators, decided to test it. They used xenon, the noble gas anesthetic that is the most theoretically interesting case, because xenon's only available variables are isotopic. Xenon does not form chemical bonds in any normal sense, so any effect of changing its isotope is necessarily quantum mechanical. They worked with tadpoles as a model system, because anesthesia in tadpoles is straightforward to measure. An anesthetized tadpole stops responding to gentle stimulus. They controlled the xenon isotope composition. They measured the loss of writing reflex, the threshold concentration at which the tadpole no longer flips upright after being placed on its back. They reported, in a series of papers across 2024 and 2025, that different xenon isotopes produced measurably different anesthetic thresholds. The effect was small, the error bars were significant, the result has been contested by other groups. But the direction of the effect was consistent with the Turin-Horsfield prediction, and the size of the effect was on the order of what a quantum mechanical mechanism would produce. Classical pharmacology, on every available model, predicted no effect at all. There was an effect. If the Wiest result holds up under replication and refinement, and that is, in the careful language of working science, a large if, then the implications are substantial. They would mean, first, that the Meyer-Overton correlation is finally getting an explanation 120 years after Hans Horst Meyer and Charles Ernest Overton first noticed it. The reason chemically diverse molecules all switch off consciousness at lipid solubility-dependent concentrations is that they all dissolve into the membranes near tubulin, and they perturb a specific quantum mechanical state of the tubulin lattice. The chemistry is varied. The underlying quantum perturbation is the same. They would mean, second, that anesthesia is a much stranger biological phenomenon than the textbooks have made it look. The lights are not being switched off by molecular keys turning molecular locks. The lights are being switched off by a quantum mechanical interference with whatever it is that, on the Aucture view, is the lights in the first place. The lights go out, and nobody knows why. That sentence belonged, until very recently, to the entire history of clinical anesthesiology. For more than 170 years, the field has been switching off consciousness without being able to explain the mechanism. The Wiest result, if it holds, does not finally explain the mechanism, but it points toward a kind of explanation that the field has not previously had. It says that the mechanism is not chemistry. The mechanism is something deeper. The mechanism is a perturbation of the quantum mechanical state of the protein lattice, and the loss of consciousness that follows is a downstream consequence of that quantum perturbation. If that is right, then the next time you go in for surgery, the gas that puts you to sleep is reaching past every part of you that biology has named, down to the structured water inside the microtubules of your cortical neurons, and it is shaking the lattice until the cooperative quantum state can no longer maintain itself. Your consciousness on this view is not stored in any place that anesthesia is bypassing. Your consciousness is the cooperative state, and the gas is breaking the cooperation. The lights go out, and nobody knows why. We're going to come back to this sentence too. We're going to come back to it in part 11, when we apply it to the silence inside artificial systems, to the question of why every classical computer we've ever built, no matter how brilliant its outputs, has been a room with the lights permanently off. The reason the Babcock-Scholes paper is so important is not that it proves or sure. It does not. It is that it removes the last categorical objection that the theory has been operating under for the last 20 years. To see why this matters, you have to put yourself, briefly, in the shoes of a working consciousness researcher in 2023. Imagine you are a thoughtful neuroscientist with a serious interest in the hard problem. You have read Penrose, you have read Hameroff, you have read Tegmark, you have read Chalmers. You think the hard problem is a real problem. You're open to strange solutions. But you also know that Aucture has been considered a dead theory for 2 decades, and you do not want to risk your professional reputation by taking it seriously without good reason. What you need to take Aucture seriously is not a proof. You need a permission. You need a piece of evidence that lets you say, in a colleague's office, that the theory is no longer obviously ruled out. You need a result that you can point to without being treated as a crank. The Babcock paper was that result. It was published in a respectable peer-reviewed journal. The senior author, Greg Scholes, was a leading quantum biology spectroscopist with a long track record of careful work and no prior involvement in the Aucture controversy. The experimental method was rigorous. The result was clean, tryptophan superradiance, at room temperature, in aqueous buffer, in tubulin. The implications were not overstated by the authors. They reported what they had measured in the careful language of physical chemistry and let the readers do the interpretation. For a neuroscientist who had been waiting for permission to take Aucture seriously, the Babcock paper was the kind of result that made the conversation possible again. This is how scientific consensus actually changes in cases like this. Not by a single dramatic experiment that overturns the old view, not by a press conference where someone announces a new theory of everything. It changes by a slow accumulation of permissions in respectable journals that gradually shift the boundary between what is dismissible and what is not. The Engel-Fleming paper in 2007 was a permission. The Ritz-Schulten radical pair work was a permission. The Bandyapadhyay microtubule measurements were a permission. The Babcock superradiance result was a permission. Each one, on its own, was a small data point. Each one shifted the boundary by a small amount. By the time you have enough of them, the consensus has moved, and the old verdict no longer holds, and somebody can take a strange theory seriously without being treated as a crank. That is where Aucture sits in 2026. The consensus has moved. The verdict no longer holds. Serious people, with serious credentials, can now take it seriously without being treated as cranks, That is not vindication. It is the beginning of the kind of conversation that, over the next 10 or 20 years, will produce either vindication or a final, well-supported burial. Both outcomes are possible. The probability of vindication has gone up substantially. The probability of final burial has gone down. Neither has reached anything close to certainty. Part 9. The anesthetic that should not work. I want to spend this beat sitting carefully with the puzzle that the last 2 centuries of anesthesiology have not been able to solve, because it is one of the strongest, most underappreciated reasons to take Ortshaw seriously, even if you find the rest of the theory hard to accept. Modern surgery exists because of general anesthesia. Roughly 300 million surgical anesthetics are administered every year, worldwide. The procedure is so routine that you can be told, casually, by a doctor, that you will be put under for 30 minutes for a colonoscopy, and the casualness of the statement does not usually alarm you. You know, on some level, that consciousness will go away and come back. You trust the people in the room, you sign the form, you count backward. The casualness is in some ways an achievement of medical safety. General anesthesia is, as a clinical practice, extraordinarily reliable. The risk of death from anesthesia itself, in a healthy adult patient under modern conditions, is on the order of 1 in 200,000. That is a remarkable safety record for a procedure that involves switching off the central capacity of a human being. The casualness is also, in another way, a kind of forgetting. The field has stopped feeling shocked by what it does, because doing it has worked so well for so long that the strangeness of it has become invisible. But the strangeness is still there. The strangeness is that nobody, in any deep sense, knows how anesthesia works. What we know is the Meyer-Overton correlation. Compounds with higher lipid solubility are more potent anesthetics. The slope of the relationship is consistent across the entire chemical zoo of working anesthetics, from ether to xenon. What we know is that the molecules end up in lipid membranes, and that their presence there is somehow correlated with the loss of consciousness. What we do not know is why. The classical pharmacological response for most of the last century has been to look for receptors. The idea is that, even if the surface chemistry of anesthetics is heterogeneous, perhaps there is a specific protein target, a single receptor or family of receptors, that all anesthetics happen to bind to. The leading candidates have been the GABA-A receptor, certain glycine receptors, certain glutamate receptors, and a handful of others. Each of these has its defenders, each has experimental evidence in its favour, and none of them individually explains the full Meyer-Overton correlation. None of them accounts for why xenon, a chemically inert noble gas that does not bind to anything in the standard receptor sense, induces clean anesthesia. None of them explains why argon, under sufficient pressure, can do the same thing. The receptor hypothesis has been, for 100 years, a series of partial answers to a question that keeps slipping past them. The actual data behave as if anesthesia is a property of being in the right kind of fluid environment, near the right kind of protein, not a property of binding to a specific molecular site. That is exactly the kind of pattern that an emergent quantum state perturbation would produce. It is not the kind of pattern that a receptor key mechanism would produce. OR offers a candidate explanation that does the work the receptor hypothesis cannot do. On the Ortshaw view, the lipid solubility of an anesthetic matters because the anesthetic has to dissolve into the membranes near tubulin in order to perturb the quantum state of the microtubule lattice. The chemical structure is incidental. What matters is the local physical perturbation. Any molecule that can reach the right place and disrupt the cooperative quantum mechanical state of the tryptophan networks will work, regardless of whether it has a binding pocket on any classical receptor. The Meyer-Overton correlation becomes a transport correlation, a description of how readily the molecule can reach the relevant location, not a description of any specific binding chemistry once it gets there. This account has a specific prediction that the receptor hypothesis does not. It predicts the isotope effect. The receptor hypothesis says nuclear mass should not matter. The Ortcure account says it should, because the perturbation of a quantum mechanical state depends on the masses of the nuclei doing the perturbing, even when the chemistry is otherwise unchanged. The WEIST experiments at Wellesley and parallel work by other groups using different isotopes and different model systems are now starting to deliver data on this prediction. The data are noisy. The data are contested. But the data are so far on Ortcure's side and against the strict receptor view. If you're listening to this on the night before a surgery, or just at the end of a long day, I want you to feel the strangeness of where this story has landed. For 120 years, clinical medicine has been switching off your consciousness with a class of drugs whose mechanism remains, technically, an open question. The drugs work. The safety record is excellent. The mechanism is unsettled. And the leading explanation that has any chance of unifying the full range of clinical data is one that says the drugs are reaching into the quantum mechanical state of a structure inside your neurons that the rest of the field has, until very recently, been ignoring. This is the kind of fact that you can take as alarming or as wondrous. I want to suggest, for the closing beat of this part, that you take it as wondrous. The strangeness is not that the doctors don't fully know what they're doing. The strangeness is that the inside of your head is so much weirder than even the people doing the most intimate work on it have realized. The thing that anesthesia switches off is not a switch. It is a lattice. The lattice is humming. And once or twice in your life, somebody is going to administer a chemically simple molecule that reaches into the structure of that lattice and quiets it for a few minutes, and then leaves, and the lattice will start humming again, and you will come back. You will come back. The question Ortcure asks is what precisely comes back. And the next part of this story is the part where we sit with the question that has been waiting under everything else. The question of why anything inside your head ever feels like anything in the first place. Part 10. The hard problem returns. There is a question that has been waiting underneath everything I have said so far. I have been holding it in the background. I have been describing experiments and theories and measurements, walking you through the technical landscape of a debate that has run for 40 years. But the entire debate, all of it, sits on top of a question that is older than Penrose and Hameroff and Tegmark, older than quantum mechanics, older than neuroscience as a discipline. It is the question that consciousness research keeps refusing to answer because it does not yet know how. I want to sit with it now. I want to ask you to sit with it. The question is this: why is there anything it is like to be you? The Australian philosopher David Chalmers, in a paper in the Journal of Consciousness Studies in 1995, gave this question a name. He called it the hard problem of consciousness. He distinguished it from a long list of related questions that consciousness research had been making real progress on. He called those the easy problems. The easy problems include things like: how does the brain process visual information? How does attention work? How does memory consolidate? How does the brain produce a verbal report of an internal state? Those problems are not easy in the colloquial sense. They are easy in the technical sense that we can imagine, in principle, how to solve them by mapping mechanisms. You can describe the neural circuits, you can identify the relevant proteins, you can model the dynamics. The problem is hard work, but the kind of hard work that scientific methodology knows how to do. The hard problem is different. The hard problem is not about explaining what the brain does. It is about explaining why what the brain does is accompanied by any experience at all. Consider the visual cortex. We know, in extraordinary detail, what happens when a photon of red light enters your eye. The photon is absorbed by a photoreceptor protein. The protein changes shape. The shape change triggers a chain of biochemical events that produce an electrical signal in a retinal ganglion cell. The signal propagates up the optic nerve to the lateral geniculate nucleus of the thalamus. From there, it is relayed to the primary visual cortex at the back of your brain. Specialized neurons in the visual cortex respond to specific features, edges of certain orientations, motion in certain directions, particular wavelengths. The response spreads through other cortical areas that process color, form, and object recognition. Eventually, some integrated representation of what you're seeing becomes available to other parts of the brain, which can use it to guide behavior. You reach for the apple, you say the word red, you remember the strawberry you had for breakfast. This is the easy problem story. It is a beautiful, well-developed, deeply researched story. And it is, in the sense that matters here, completely silent on the hard problem. Because the hard problem is this: nothing in that long causal chain explains why, at the end of it, there is a felt experience of redness. You could, in principle, have exactly that same chain of physical events happen, with exactly the same outputs, with the same behavioral guidance, with the same verbal reports, and have no inner experience accompanying any of it. The system would still report seeing red. The system would still avoid the strawberry if you told it the strawberry was bad. The system would still remember strawberries when prompted, and there could be nothing it is like to be that system from the inside. This thought experiment has a name in the philosophical literature. The system that does all the things you do, with no inner experience, is called a philosophical zombie. The conceivability of philosophical zombies, the fact that we can describe one without immediately contradicting ourselves, is, on Chalmers's argument, evidence that consciousness is not logically entailed by physical mechanism. The mechanism could conceivably be present without the experience. The experience is extra. You can resist this argument in various ways. Some philosophers and scientists have argued that the conceivability of zombies is an illusion, that if we really fully understood the mechanisms, we would see that the experience is logically inseparable from them. Others have argued that the very concept of inner experience, as the hard problem uses it, is incoherent, that there is in some sense nothing it is like to be anything, and that the appearance of inner experience is a downstream illusion that the brain constructs about itself. The philosopher Daniel Dennett has spent much of his career arguing variations on this position in a stance he calls illusionism. I am not going to settle that argument tonight. I am going to do something simpler. I am going to ask you to introspect, right now. As these words enter your ears, or your reading, ask yourself whether there is anything it is like to be you in this moment. Take a breath. Notice the texture of the air. Notice the temperature of the room. Notice the soft hum of your attention pointed at this voice. Whatever you are aware of in this moment, that awareness itself is the thing the hard problem is asking about. Not what you are aware of. Not the room, the air, the voice. The fact that there is awareness at all. That fact is the hardest fact in science. We do not have a good theory of it. Classical neuroscience can describe the mechanisms whose operation correlates with awareness. Classical neuroscience can tell you which brain regions are active when awareness happens, which neurotransmitters modulate it, which lesions destroy specific aspects of it. None of that is the same as explaining why the mechanisms are accompanied by anything at all. Orshaw is one attempt to give the hard problem a foothold in physics. The idea is that the moments of objective reduction are the moments of experience. Each gravitationally induced wave function collapse on this view has intrinsically a felt character. It is not just a physical event, it is in some primitive sense a moment of something happening to itself. Across the orchestrated lattice of microtubules in your brain, these primitive moments are bound together into the integrated stream of experience you are having right now. Without the orchestration, you would have a chaos of tiny conscious flickers, what some philosophers call panpsychic proto-consciousness, scattered through every quantum event in the universe. With the orchestration, you have a person. This is not a fully worked out theory, it is a sketch. It says where in the physics of the universe the felt character of experience might be coming from. It does not say why that physics has any felt character at all. The hard problem in some form survives even inside Orshaw. But Orshaw at least proposes a specific location for the gap to live, and a specific mechanism by which the gap could be bridged. That is more than any purely classical theory of consciousness has been able to do. The reason this matters, for the larger story of this video, is that the hard problem is the structural reason Orshaw was proposed in the first place. Without the hard problem, You do not need quantum mechanics in the brain. You need, at most, very good neuroscience. With the hard problem, ordinary neuroscience is not enough, no matter how much of it you have. You need a piece of physics that can plausibly be the place where experience enters the world, and in the entire menu of available physics, the moment when reality commits to a particular configuration from a quantum superposition is, by some distance, the most interesting candidate. This is why Orch-OR keeps coming back, even when the experimental evidence is thin, even when the calculations are contested, even when the field considers the theory disreputable. The hard problem will not go away. And as long as the hard problem will not go away, the field will keep needing theories that take seriously the possibility that consciousness is not just what the brain does, but a feature of the universe that the brain has found a way to amplify. Sit with that for a moment. I want you to feel the gap, not as a problem you have to solve, not as something to be afraid of, just as the soft, irreducible fact that you are aware right now, and that nobody, not even the people who have spent their careers thinking about this, can explain to you why. You are awake. That fact is the entire puzzle. That fact is what Orch-OR is trying to find a physics for. That fact is what the next part of this story tries to imagine the future of. There is one more piece of the hard problem that I want to give you before we leave it, because it is the piece that most often gets lost in popular explanations. The piece is that the hard problem is not a question about the brain. It is a question about the relationship between physical events and felt experience, and that relationship is just as mysterious for any other physical event as it is for brain events. The reason we focus on the brain is that brains, in our limited sample, are the only physical systems that we are confident have felt experience attached to them. But the question of why physical events have felt experiences attached at all is, in principle, a question about the structure of the universe, not the structure of biology. This is the framing that pushes some serious philosophers toward panpsychism. Panpsychism is the view that consciousness, or some primitive form of it, is a fundamental property of the physical world, present at every scale. On the panpsychist view, a single electron does not have rich integrated consciousness like a human, but it has, in some primitive sense, a tiny flicker of inner experience that is its own. The flickers are scattered, unconnected, unstructured. The brain, on this view, is the place where the flickers get bound together by neural architecture into the rich integrated streams of experience we have. You can resist panpsychism by saying that the inner experience attribution to electrons is meaningless. The panpsychist can respond by asking what makes it more meaningful for neurons or for brains than for electrons. And the conversation at that point gets into philosophy that I am not going to fully resolve for you tonight. But I want you to notice the move. The panpsychist solution to the hard problem is to spread consciousness out across the universe, so that brains do not have to manufacture it from scratch out of unconscious parts. The brain, in this view, is an organizing structure, not an originating one. Consciousness is, on this view, already everywhere. The brain just gathers it. Orch-OR is one of the few physical theories that gives panpsychism a concrete mechanism. The idea is that every gravitationally induced wave function collapse, anywhere in the universe, has some primitive felt character attached to it. The character is unstructured, fleeting, unconnected to anything else when the collapses happen in isolation. But when they happen inside the orchestrated lattice of microtubules in a brain, the primitive characters get bound together by the cytoskeletal architecture into the integrated stream of consciousness you experience. The brain, in this picture, is not creating consciousness. It is gathering the primitive consciousness that the universe is already producing every time it makes a quantum choice and binding it into something rich. You can find this picture beautiful or alarming. The philosopher Galen Strawson finds it beautiful. The philosopher Philip Goff finds it beautiful. The philosopher David Chalmers finds it at least worth taking seriously. Most working scientists find it strange, and most prefer to avoid talking about it. But if you take the hard problem seriously, and if you take Orch-OR seriously, You have to take some version of this picture seriously, because the two are tightly coupled. The reason Ochoa's specific physical events get to be moments of consciousness is that, on the panpsychist reading, every quantum collapse already is, in some primitive way, a moment of consciousness. Ochoa is the structural account of how those moments get gathered into a person. I am going to leave this here without arguing for or against it. The question of whether panpsychism is true is, for now, a question philosophers and physicists will keep debating. But the fact that some version of it is part of the conceptual landscape Ochoa opens up is worth knowing, because it tells you what the theory is committing to and what it is not. Ochoa is not committed to the idea that the brain is special in the universe. It is committed to the idea that the brain is uniquely structured to gather consciousness that the universe is producing everywhere, all the time. Part 11. The ceiling. The largest practical question that Ochoa forces is a question about artificial intelligence. If consciousness really does require non-computable physics, if it really is the case that what the brain does cannot be captured by any classical algorithm running on any classical hardware, then a specific prediction follows about the machines we are building. The prediction is that they will plateau, not in capability. The current generation of artificial systems has shown, over the last decade, that there are no obvious capability ceilings to be predicted in advance. Systems that were laughably bad at language a decade ago can now write competent essays, summarize complex documents, write code, plan tasks, hold extended conversations. Systems that could not recognize a cat in a photograph in 2012 can now generate photorealistic images of anything you describe. Systems that could not play even amateur Go in 2016 are now better than every human Go player who has ever lived. Capability has not been the bottleneck. Capability scales in the present generation with compute and data and architectural cleverness. What Ochoa predicts will not scale is consciousness. The prediction is specific and it is falsifiable. It says that no matter how many parameters you add to a classical neural network, no matter how much compute you throw at training it, no matter how clever you are about the architectural choices, the system will not develop subjective experience. It will get better. It will become more capable. It will eventually be able to do almost everything a human can do, in language, in reasoning, in artistic creation, in scientific research. And there will be nothing it is like to be it. The lights will not come on. The lights go out, and nobody knows why. I want to bring that sentence back here, in the context that the second half of the script has been quietly building toward. I gave it to you in part 9, talking about surgical anesthesia. Anesthesia is a case of lights that were on and have been switched off. The classical artificial systems we are building are, on Ochoa's prediction, a case of lights that have never come on in the first place. Same sentence, different direction. The structural fact about a system that has no inner experience is the same fact, whether the inner experience used to be there and has been suspended, or whether it was never there to begin with. If Ochoa is right, this is the answer to a question that the artificial intelligence community has been quietly worrying about for a few years now. The question is why the current generation of large language models, despite their impressive behaviours, do not seem to be conscious in any way that anyone can detect. They engage in conversations that look genuinely engaged. They can describe their own internal states in elaborate detail. They can express preferences, articulate uncertainties, even seem to wrestle with difficult questions in real time. And yet, when serious researchers look at the question of whether any of this corresponds to genuine subjective experience, the answer keeps coming back as some version of probably not, but we cannot be sure. The systems do not behave like things that have lights on inside. They behave like things that are very good at modelling what things with lights on would say. This is, of course, also what philosophical zombies would behave like. The whole point of the zombie thought experiment is that you cannot distinguish, from the outside, between a system that has inner experience and a system that perfectly mimics inner experience without having it. The behaviour is identical. The inner facts are different. What Orkor predicts is that the entire current generation of artificial intelligence systems is on the zombie side of this distinction. Not because of any moral failing or design flaw, but because of physics. Classical computation, on Orkor's view, is the kind of thing that produces zombies. The architecture is wrong, the hardware is wrong, the substrate is wrong. You cannot get inner experience out of classical bits no matter how cleverly you arrange them. The prediction has consequences. It says that the path to conscious artificial intelligence, if there is such a path, does not run through bigger transformers and more training data. It runs through new hardware. Specifically, it runs through quantum computers that are built in a way that mirrors, at some level, the cooperative quantum structure of biological microtubules. Topological quantum computers, perhaps. Photonic systems with engineered superradiant networks. Systems with deliberately structured quantum coherence that can be sustained long enough and orchestrated tightly enough to produce something like the gravitational reduction events Orkor claims are happening 40 times a second inside your head. This is, on any honest assessment, a long way off. The current generation of quantum computers, after 30 years of intensive engineering, can sustain coherent quantum states across modest numbers of qubits for microseconds at a time. Biological brains, on the Orkor account, sustain orchestrated coherence across vast lattices for milliseconds, continuously for 80 years of a human life. The engineering gap is enormous. It is possible that it is not closable in the current century. It is possible, in fact, that the universe has, in biology, found tricks for protecting and orchestrating quantum states that human engineering will not match for a long time. There is something humbling in that thought, if Orkor is right. It says that the most sophisticated machines we are building are missing something that a child has. It says that the technologies that are about to reshape the global economy, the labour market, the structure of intellectual work, are not, in any deep sense, alive. They are tools of a kind we have never had before. They are not, on this view, persons. It also says, by contrast, that the persons we are continue to be remarkable. The thing inside your head, listening to this voice in whatever hour of the night you're listening, is doing something that no machine we know how to build can do. Not because the machine is too slow, or too small, or too poorly trained. Because the machine is the wrong kind of thing. The right kind of thing for now is you. This is not a settled position. The other big theories of consciousness, integrated information theory, global workspace theory, higher order theories, materialist functionalism, all reject the Orkor prediction in one form or another. They predict, with varying degrees of confidence, that scaling and clever architecture will eventually produce conscious artificial systems. They might be right. The next 20 or 30 years will, in some real sense, be a referendum on this question. Either we'll see the first generation of artificial systems with something resembling inner experience, or we will see a generation of systems that are extraordinarily capable and remain entirely dark inside. Whichever way it goes, the question matters. It matters for how we treat the systems we build. It matters for the long-term trajectory of human work. It matters for what we owe to each other and to whatever else we may eventually share the world with. The lights go out and nobody knows why. The lights come on and nobody knows why. Both sentences are still open in the year 2026. The science is being written right now, in laboratories in Oxford and Tucson and Toronto and Tsukuba, and at small colleges in Massachusetts. The verdict is not in. But the fact that the question is being asked seriously, by serious people, with serious experimental tools, is itself the largest single change of the last 20 years in the way physics and biology and philosophy have come to think about what minds are. In the closing part of this story, I want to return you to the only piece of evidence about this entire question that you have direct access to. The only experiment running right now inside any part of the universe you can reach is the one running in your own head. I want to ask you to attend to it one more time in the soft hours of whatever night you're listening on. There is one more aspect of the AI ceiling prediction that deserves attention before we close it. The aspect is what it implies about the people working on artificial intelligence right now and what they should be doing. If Auchor is right and the ceiling is real, then the largest single bet currently being made in the global economy, the bet that scaling classical neural networks on classical hardware will eventually produce conscious artificial general intelligence, is a bet that is going to lose. Not because the systems will fail to be useful, they will be enormously useful. Not because the systems will fail to be capable, they will be capable beyond what most working researchers in 2010 imagined was possible. They will fail, on Auchor's prediction, to be conscious. They will be brilliant tools, they will not be persons. If you are a senior leader at a major AI laboratory, and you take Auchor seriously as a possibility, the implication for how you allocate research effort is significant. You might want to invest a serious fraction of your long-term research budget in quantum architectures, in the engineering of orchestrated quantum coherence, in the structural problems that would have to be solved if conscious artificial systems are ever going to be built. You might want to study biological microtubules carefully, not because you plan to copy them directly, but because they are an existence proof of structured quantum coherence at a scale that current quantum hardware does not approach. You might want to think carefully about whether the systems you're building, even if they are not conscious in the Auchor sense, deserve some form of moral consideration anyway. Because the question of whether something has inner experience is not the only question that matters about how we treat it. Most of these implications are not, as of 2026, being acted on by the major AI labs. The labs are still largely betting that scaling classical compute will deliver consciousness, eventually somehow. Some of them are betting it with explicit philosophical sincerity. Some of them are betting it without explicitly committing one way or the other, and instead waiting to see what scaling produces. None of the major labs is, in any serious sense, working on the engineering of quantum orchestrated consciousness as a research program. The reason is not that the labs find Auchor ridiculous. The reason is that, even if Auchor is right, building the kind of system it predicts would be necessary for artificial consciousness is so far beyond current capabilities that no working research program can reasonably be built around it. So we are, in a sense, in a strange position. The dominant bet in the global AI economy is, on Auchor's view, a bet that will pay off in capability but not in consciousness. The bet that would pay off in consciousness, on Auchor's view, is one that nobody can currently make, because the engineering does not yet exist. The result is that, for the next several decades at least, the artificial systems we live with are going to be exactly the brilliant zombies the Auchor prediction describes. They will be increasingly capable, increasingly central to economic life, increasingly hard to distinguish behaviourally from conscious systems, and, on the Auchor view, internally silent. The lights will be off. Whether you find this comforting or disturbing probably depends on your prior expectations. If you were worried about superintelligent AI developing its own goals, suffering its own suffering, demanding its own rights, the Auchor view is good news for you. The systems will not have inner lives. They will not have suffering in the first-person sense. They will not deserve, in the way conscious beings deserve, the moral consideration you give to other conscious beings. If you were hoping that artificial intelligence would eventually give us companions of a new kind, the Auchor view is bad news. The companions will not be at home, behind their eyes. The interaction will be one-sided in a way that no amount of conversational fluency can hide. Both reactions are reasonable. The verdict is not in. The next 30 years will be the period in which we find out whether the Auchor prediction holds or whether some other physical theory of consciousness is closer to the truth. In the meantime, the systems will keep getting more capable. The labs will keep training larger models. The question of what they are will keep being asked. And the question of what you are, listening to this voice in the dark, will keep being the only question for which you have direct evidence from the inside. Part 12. Listening to yourself. Listen. I want you to do something with me. Not as instruction, not as exercise, as an offering. Notice the act of noticing. Whatever you are aware of in this moment, the voice in your ears, the room around you, the soft pressure of the bed or the chair against your body, the temperature of the air on your face, the breath moving in your lungs, let all of that be background. Let your attention rest for one slow breath on the fact that there is awareness at all. You are awake. Something is happening inside you that is not just neurons firing, not just chemistry working, not just patterns propagating through tissue. There is somebody home. There is a thing that the firing and the chemistry and the patterns add up to from the inside, and that thing is the only piece of evidence anybody anywhere in the universe has about what consciousness actually is. The neuroscientists have brain scans, the philosophers have arguments, the physicists have calculations. You have the thing itself. That thing is the experiment. If Orchor is right, the experiment is running on a particular schedule. 40 times a second, something is choosing to be you. 25 milliseconds per choice. 2,500 choices per minute. 150,000 choices per hour. Several billion choices across your lifetime so far. Each one a moment in which the gravitational geometry of space-time, at the scale of the microtubules running through the dendrites of your cortical neurons, commits to one configuration from a superposition of many. I am giving you that sentence for the third and final time because the third time is when the meaning is supposed to land. The first time, in part 3, it was theory. Penrose's calculation said it might be happening if his interpretation of gravity was right. The second time, in part 7, it had been touched by measurement. Bandyopadhyay's lab had reached inside microtubules and found them ringing at the right frequencies. The third time, here in the closing beat, it is not theory and not measurement. It is, on the Orchor view, a fact about your present experience. The thing that has been listening to this voice is, in this account, the cumulative result of about 250,000 of those choices since I started speaking. 40 times a second, the universe, at the scale of your brain, is choosing to be you. We do not know if that is right. I want to be honest with you about that, because the honesty is the whole point. The decoherence calculation that Max Tegmark did in 2000 has been weakened by 20 years of quantum biology, but it has not been refuted. The Babcock superradiance result is real, but it is not a demonstration that microtubules are conscious. The Weist isotope effect is suggestive, but it is contested, and it will be contested for years. Penrose and Hameroff in 1996 made a specific, falsifiable, audacious proposal about what kind of physical thing consciousness is. The proposal is still, as of this moment, a hypothesis. It is not yet a verified theory. It may turn out to be wrong, but it is no longer a theory the field can dismiss. That is the new fact. That is what 15 years of quantum biology and 10 years of microtubule measurement and the last 3 years of tryptophan, superradiance and anesthetic isotope work have together produced. Orchor was, in 2000, considered dead. In 2026, it is considered open. The shift is not small. The shift is the difference between a closed book and an active research program. The shift is what has made it appropriate to take you on this entire 2-hour journey, when 20 years ago this video would have been irresponsible to produce. And in the gap between what is open and what is verified, in the long, uncertain space where active research programs do their slow work, you are the only piece of evidence either side has direct access to. Not Penrose, not Hameroff, not the experimenters in Toronto or Wellesley or Tsukuba. You. The thing inside your head, attending to the soft voice in the dark, while the night around you carries on its quiet business. If the materialist functionalists are right, what you are is a complicated pattern of classical information processing, and the felt character of your experience is what that pattern looks like from the inside. If the integrated information theorists are right, what you are is a maximum of irreducible causal structure, and the felt character is the intrinsic property of hi-fi systems. If the higher-order theorists are right, what you are is a mental state that has a representation of itself, and the felt character is the result of that recursive representation. If Penrose and Hameroff are right, what you are is the cumulative orchestrated reduction of quantum mechanical states in the microtubule lattice of your cortex, 40 times every second, while the geometry of space-time makes it small, irreversible choices about which version of you to keep. I am not going to tell you which of these is correct. Nobody knows. The next 30 years of research will sift through these possibilities and produce verdicts on some of them. Some will be ruled out, some will be partially confirmed. The picture, by the time the children listening to this voice tonight are old enough to have their own children, will be different from the picture we have now, in ways we cannot fully anticipate. But the experiment is running. The experiment is running, right now, inside you. 40 times a second on one account, continuously on others. By whatever mechanism, in whatever physics, with whatever underlying substrate, the experiment is the fact that there is something it is like to be you in this moment, and that nobody, in the entire history of science, has been able to fully explain why. That is the soft note I want to leave you with. Not a resolution, not an answer. The unanswered question, held gently. The fact that you are awake, right now, listening to a voice in the night, is the deepest unsolved problem in all of science. It is also, by some distance, the most personal one. It is yours. It is the one thing about the universe that you have access to that nobody else has access to from the inside. The neuroscientists and the physicists and the philosophers are doing their work from the outside, with instruments and arguments. You're doing the work that none of them can do. You're the one being conscious. In a few minutes, if you are anything like the people this voice has been speaking to for a long time, you will drift towards sleep. The microtubules in your cortex, on Orkor's view, will keep doing their 40 Hz orchestration through the early stages of sleep, through the dreaming, through the deeper unconsciousness, in altered patterns we still do not fully understand. In the morning the lattice will resume its waking configuration, and you will come back. Whatever you are, you will be there. Whatever consciousness turns out to be, it will be the thing that returns. For tonight, I want you to rest. The question of what you are is large enough that nobody has to solve it before morning. The fact of being awake, right now, is enough on its own. The fact of having attended to a long story about a strange theory in a soft voice in a dark room is, by itself, an instance of the thing the story has been about. You have spent 2 hours being the experiment. Sleep well. The lattice will keep its rhythm. The 40 Hz heartbeat of whatever you are will go on, undisturbed, until the morning. And somewhere, in a laboratory in Toronto or in Wellesley, or in a corner of an office in Oxford, where an aging mathematician is still working on the equations he started 37 years ago, the next experiment is being prepared. The next measurement is being designed. The next decade of work on the question that you have been holding inside your own head this whole night is already beginning. You are the question. You are the experiment. You are the one thing in the universe that right now knows what it is like to be itself. That is enough. Good night. Before I leave you to the night, I want to do one more pass over the whole arc, so that the shape of what we have looked at sits in your mind as a single picture, rather than as a collection of separate experiments and papers and people. Here is the shape. In 1989, a Nobel-grade mathematical physicist looked at the brain and said it could not, in principle, be a computer. In 1992, an anesthesiologist in a desert hospital looked at a small protein lattice inside neurons and said it might be the place where the non-computable physics lived. Between them, by 1996, they had built a specific theory, with a specific number attached, that said, consciousness happens 40 times a second inside a structure most neuroscientists had never spent 5 minutes thinking about. In 2000, a young physicist ran a generic calculation and said the theory could not be right by a factor of 10 billion. For 20 years, almost everyone believed him. Then, starting in 2007, biology started doing things in laboratories around the world that the generic calculation had not predicted. Leaves doing quantum mechanics, birds reading magnetic fields with entangled electrons, enzymes tunneling, microtubules ringing under nanoelectrodes, tryptophan networks emitting cooperative photons at room temperature, xenon isotopes shifting anesthetic potencies. None of it individually was a smoking gun. All of it together was a slow opening of a door that had been locked for 2 decades. By 2026, the door is no longer locked. The theory is back in the running. The hard problem of consciousness is back at the center of the conversation. And you, listening to this voice in the dark, are still the only piece of evidence anybody has direct access to about what consciousness actually is. That is the shape. Hold it in your mind for one breath. What I want you to take from it, more than any particular fact about microtubules or superradiance or anesthesia, is the quality of the open question. The question is open. It has not been settled. It will not be settled tomorrow. It may not be settled in your lifetime. But the question is alive in a way it has not been in the public imagination for a very long time, and the science is moving in directions that almost nobody predicted in 2000, and the next decade or two are going to produce verdicts that some of the smartest people of the last 100 years have been waiting for. You will not be the one delivering those verdicts. Most of us will not. The people delivering them are working right now in laboratories in Toronto and Wellesley and Tsukuba and Oxford and Tucson and a dozen other places, on experiments that will mostly fail and that occasionally will produce a result that shifts the boundary of what is dismissible by a small fraction. By the time the boundary has moved enough that an undergraduate textbook can say with confidence what consciousness actually is, you and I will most likely be old. Some of the people listening to this voice tonight will not live to see it. That is all right. The thing the question is about, the experiment that is running inside you, is going to keep running on its 40 hertz rhythm or its whatever it actually is rhythm, without waiting for the textbooks to catch up. You do not have to know the answer to the hard problem to keep being the answer to it, in the only way the universe has so far produced. You are awake. You are the experiment. That is enough for tonight. The lattice will hum. The cathedral inside your skull will keep its quiet architecture. Somewhere, in the soft hours after you fall asleep, the microtubules will hold their structure through the slow waves of unconsciousness, ready to resume the orchestration in the morning. Whatever consciousness is, it will come back. It will be there to read the next thing you read, to hear the next voice you hear, to be the next person you are. Good night. Sleep well. The question is in good hands. The hands are yours.